All right, I told you we were going to do this one-dimensional interference 3 ways. We've done it 2 ways. Now we're on our last one. Okay, so again, we're going to use the principle of superposition. Are you surprised? All right, 3rd time I've shown you this picture, correct? So again, 2 identical waves except for different phase factors. By the way, sometimes I call this a phase factor, sometimes I call it a phase constant. Same thing, but just don't get it confused. This is the phase factor or phase constant. This whole argument of the sign is the phase. So don't get them confused or you're going to have all sorts of problems. All right, so what we want to do, we just want to add them, right? We want to use the principle of superposition. We're going to add these things. Now, you remember a little while ago, we added, when we were talking about the standing wave, we had sine kx minus omega. We didn't have this, right? So we just had this and this. And we had to use those addition and subtraction formulas from trig. And that wasn't too bad. But now we have 3 terms, right? So that's going to be a pain. And we're not going to do it. Sorry, if you want to do it, you're welcome to it. But I'm not going to do it. So basically what you do though, you just look at this as one term, this is the other term, you use the addition formula, then you do it again. You just do it twice, right? Not a big deal, but it gets kind of messy. But we could do it, I just don't want to. All right, so what you do, you use all the trig relations and you just add them. And then you wave your hand and there's the answer. All right, so I promise you this is just, you could do this. All right, so using your trig relations, this is what you get. You get 2a cosine delta phi over 2 times sine kx average minus omega t plus phi 0 average. And this is a constant, right? So just call it a constant. Okay, there you go. Pretty lazy, huh? Now, so again, this is just a constant times a sine. Now remember, when we're talking about standing waves, I asked the question, is this a standing wave? And the answer was no. Now this, we have 2 waves going in the same direction. This is the answer, right? Is this a standing wave? Is this a traveling wave? Sorry, traveling. Is that a traveling wave? Well, of course it is. It's a function of kx minus omega t, right? A standing wave is not a traveling wave, because it wasn't a function of kx minus omega t. This is a function of kx minus omega t, so it's a traveling wave. All right, awesome. Now, let's just do our little questions again and just go from what we learned earlier. All right, so again, I think it would be best, answer these questions, do it conceptually first, use the formula second, okay? All right, so two waves. Let's say that the phase difference is 0. Well, now you're thinking I'm totally stupid because we already know the answer, right? If the phase difference is 0, it's in phase constructive interference, correct? So you just add them. No kidding, right? You just add them. All right? I mean, no kidding. What a dumb question, but that's okay. That's okay. All right? So here the amplitude is A. Here the amplitude is A. If they're in phase, constructively interfering, we're going to add them. The amplitude is going to be 2A. Ta-da! 2A. All right? No kidding. Okay, let's use the formula. Sorry, let's use the formula. All right, if delta phi is 0, then this is 0, cosine of 0 is 1, so we get 2A, blah, 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 blah. 2A, blah, 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 blah. So it works. All right, let's say this. Let's say the phase difference is pi. We already know. If the phase difference is pi, out of phase, destructive interference, right? Destructive interference, the displacement is 0. Okay, now we just know that from what we've talked about. Let's put it in the formula. Delta phi is pi. This would be pi over 2. What's cosine of 90? 0. So this is 0. All right? So there you go. Okay, that's all. And of course, then you can do it. You can use this formula for anything you want, right? Anything in between. But all I'm saying is you get the same results as the last time, which was the same results as the first time. So we've done this 3 different ways. You get the same answer for each of the 3 different ways. And it all agrees with the data, so the theory is correct. Yay! All right, we're done with that. We're not done. All right, so I started off this chapter by showing you this picture. And this is called a thin film. This is an air bubble, right? So it's a thin film. You know that bubble part? It's very thin, okay? So a thin film. So what we want to do is we want to explain these thin films using the wave theory of light. And I promise you, I sort of like this for some weird reason, so I promise you there'll be one of these on the test. Promise. Probably on the final also. So you want to make sure you understand this. And we'll do plenty of examples so you will understand it, hopefully. All right, but before we do it, we want to develop a helpful, hopefully, a helpful analogy between rope and light waves. Okay? So here we go. So here's a rope wave. So here, okay, so this is called a fixed end. So this rope is somehow attached to this to the wall. So we have this arriving pulse. And what does it do? It flips, right? So here we have a up, here we have a down. So when you have a fixed end, the wave pulse flips. Okay? Nice. Now, let's do it with a free end. So now you can see that the rope is attached to some circular thing, and this is free to move. So you have the pulse coming in, and what happens? Does the pulse flip? Does it invert? No, it doesn't invert at all. Okay, so there's the difference. So the difference is here, for the fixed end, the reflecting pulse is inverted. I say flipped. Here with the free end, the reflecting pulse is not inverted or not flipped. All right? So sometimes it flips and sometimes it doesn't. That's really the important thing. Okay. Now, okay, I just showed you this, right? I mean, something similar. Again, fixed end. So fixed end is inverted or flipped, right? So before, after. So the reflected pulse is inverted, the amplitude is unchanged, it's just inverted. Okay, now here's a hard question. For a sine wave, here's a sine wave. Now, if I wanted to flip it, right, if I wanted to invert it or flip it, so how could I flip this thing? How could I flip a sine wave? In terms of phase change, okay? How could I change a sine wave, invert it with a phase change? What's phase change? Okay, if I put a phase change of 2 pi, it would look exactly the same, right? If I had a phase change of pi, what would it look like? It'd be flipped. Agree? It'd be flipped. In other words, it would look like this, All right? It would look like that. Okay? So all I'm saying is, if I'm going to get a sine function to flip or to invert, I need a phase change of pi. All right? So phase change of pi is going to flip it. Now, remember, how do you make a phase change? 2 ways. Path difference and phase constant difference. Okay? Now, here, it's the same wave. I mean, the same piece of rope. So you can't have a phase constant change because it's only one rope. Okay? So what's going to be equivalent to this? If we can't change the phase constant, what's the only other thing? The path length, right? The path length. Okay? Now, what path length is going to flip this guy? Okay, if we have a path length of a 1 wavelength, it's going to look the same, right? If we have a path length difference of a half a wavelength, what's it going to look like? Like it's flipped. So what I'm saying then is that a phase difference of pi is equivalent to a path length difference of a half wavelength. Now, you have to understand that logic. So if you don't understand that, turn off your video, go back, think about it, listen to it again, whatever. But this is the crucial point, okay? To flip a wave from up to down or down to up, it's equivalent to this, which is equivalent to this, because we can't change the phase constant. All right? Okay, awesome. Oh yeah, by the way, this agrees with our formula that we figured out a while ago, right? Remember we showed that earlier? Okay, we know that this is 0 because it's only one wave. So if we want to change this by pi, it means that this is a half a wavelength, because we'll have a half here, 2 pi here, 2 pi times a half is pi. Yay! All right? All I'm saying is it all is consistent, all right? It all makes sense and it's all consistent. Okay? All right. Now, all right, so we've been talking about ropes, but I thought we're talking about thin films with light. So again, this is hopefully supposed to be a helpful analogy. Maybe, I don't know. Okay, let's talk about light. All right? This is just a reminder. We had this a while ago. Remember, light slows down when it goes through a medium, like glass or water. So n, the index of refraction, is c, which is the speed of light in the vacuum, divided by v, which is the speed of light in the medium. And then we learned that the wavelength was changed. The wavelength of light in the material equals the wavelength of light in a vacuum, divided by the index of refraction of the material. And remember that? All right, here's the important thing. All right, here's the important thing. Are you ready? Here's the important thing. All right. When light travels from a low n, like let's say vacuum, to a higher n, like glass, look what happens. Look what happens. Here's a up, here's a down. It flips. When light goes from a high n, like glass, to a low n, like a vacuum, it doesn't flip. Okay? So let's read it. Light waves are inverted, which is equivalent to a phase change of pi, which is equivalent to a path difference of lambda over 2. When reflected from a medium, see, this is reflected, right? Okay? When reflected from a medium of low n to high n, right? So that's like that rope, you know? Remember the rope? Where's the rope? Okay, the rope was when it went to a fixed end, right? It flipped, all right? So that's supposed to be the analogy, okay? So light waves are flipped, which is equivalent to a path difference of lambda over 2 when it's reflected, only reflected, from low n to high n, all right? That's it, okay? When it goes from high n to low n, nothing happens. Nothing happens. Okay, now, oh yeah, okay, whatever. All right, so this is the analogy, right? Low to high is like a fixed. High to low is like a free end, all right? There's your analogy. Thank you. Okay, now we've got to go to thin films. All right, so look. Here's an incident beam of light. This is a thin film. Maybe it's a thin sheet of plastic, or maybe it's some like reflective coating, or who knows what. It's a thin film, you know? And here's like maybe glass, or who knows whatever, right? Oh, no, this is air, sorry. So this is air. This is a thin film of who cares what, and it's greater than 1. Here's glass again. Okay, here's an incident beam. There's going to be 2 places where the light reflects. The first one is here. Bingo! It reflects. Then it's going to go through. I don't care about, okay, look, we're going to be totally lazy, all right? I don't care about the angle here. I don't care about any of this garbage. All I want to know is light's going to go through the film and reflect again. Okay? So I don't care about all these details. I don't care about this guy. I don't care about these angles. I don't care about this guy. All I care about is that there's a reflection here and there's a reflection here. We'll learn all these details later on, I promise you. But now, we're going to be totally lazy. Reflection 1, reflection 2. Now here's the thing. Here, for this guy, it's going from n equals 1 to n greater than 1, right? So it's going from low n to high n. So what's going to happen? It's going to flip, right? It's going to flip. So you're supposed to see that, right? So here's an up and here's a down. Flip. Here, it's going from high n to low n, so no flip. See? No flip. All right? So there it goes. That's how it actually works. All right. So again, this is what you want to remember. Oops. It only flips from low to high. Low to high. All right. Now, oh boy. All right. Now what we want to do is we want to do a thin film. Example. Okay. So, the first thing you want to understand, this is a totally exaggerated but useful diagram. Right? Totally exaggerated. But you're going to see that it's useful. So that's all I care about. I mean, typically, you'll read some of the problems in the tests and the homework and all that. What they usually say is that this light is coming in perpendicular to the film here. But when you draw it perpendicular, it's really hard to analyze it well. So we're just going to exaggerate it crazy. All right. So this is what we're saying. So there's only one incoming wave. So the one incoming wave is this guy. It reflects here. Then it goes through. And I don't care about this angle. You can just draw this straight as far as I'm concerned. So it goes through, then it reflects here. All right? And what we want to see is how this guy, this reflected wave here, and this reflected wave, how they interfere. All right? Now also, just to show you how ridiculous this drawing is, so this is a coating, right? Some kind of thin film. So obviously, number 2 travels down and back, so more distance to number 1, right? So there's a path difference, agree? So the path difference, we're going to say, is the thickness of the film, up and back. Well, you look at that and say, Brother Weber, you're crazy. Because obviously this distance is longer than this distance. But remember, this is a totally exaggerated drawing, right? Totally exaggerated, okay? So again, we're saying that this distance here is just equal to 2t. And in reality, it really is. We're just exaggerating this wildly just to make it easy to analyze. Okay? All right, so that's our goal. All right? Our goal is to see how this reflection interferes with this reflection. All right? And that's all there is to it. Not a big deal, you know? Now, well, it is a big deal. So what is going to cause different kinds of reflection? Interference. Well, there's a path difference, right? Number 2 travels 2t more than number 1. So a path difference results in a phase difference. Phase differences result in interference. But there's something else as well. There's different ends, right? And air and film and whatever. And so, when you get a reflection from different ends, you can throw in another phase difference, right? It could be a flip or it could be not a flip. It could be a phase difference of a pi, which we're going to say is a lambda over 2 flip, or no flip. Okay? So there's 2 things going on. There's the path length difference, or however you want to put it, and there's different places where the light is reflecting. Okay? So there's 2 ways that things are going to get messed up, or I shouldn't say that. There are 2 reasons for the interference, the path length difference and the different indices of refraction. Okay? So there you go. And look there's only one wave coming in, so we don't have to worry about this, right? Right? There's no difference in phase constants because there's only one wave. So this is true. So we don't have to worry about it. All right? All we have to worry about are the different path lengths and what happens at the reflections. That's all you have to worry about. Okay. Are you ready? Let's do it. All right. Oh boy, here we go. Now again. All right. Okay, so again, the path delta x, which is the path difference, is always going to be 2t. So, all right, always. So again, I know I already said this, but just pretend that the light is really coming in perpendicular, So just pretend this is really 2t. All right. Okay, here we go. Now, so we're going to fill in this table. And this is not something to memorize. You have to understand it. So we're going to work out this table for constructive interference, and then we're going to do it for destructive interference. And again, this is nothing to memorize. All right. So let's say that the problem says they want to know, what they typically say is, what is the thickness of the film so we can have either destructive interference or constructive. So let's just assume for this, we're going to assume that we want constructive interference, all right? We'll do destructive in a couple of minutes. So we want this guy and this guy to constructively interfere, okay? All right, now look, we have one reflection, two reflections, right? And so, without knowing the ends, we don't know if there's going to be a lambda over 2 flip here or here, right? We don't know. So we're going to discuss every single case and just see what the conditions are. That's all. All right. So again, we want constructive interference. Now, let's just assume that there are no flips. All right? No flips. So this n is bigger than this n, and this n is bigger than this n. All right? Okay, so no flips. Okay, well, if there's no flips, and we want constructive interference, what's the path difference? Okay, now think about it. There's no flips. We want constructive. So doesn't this path difference have to be like 1 wavelength, or 2 wavelengths, or 3 wavelengths, or 4 wavelengths? Well, yeah, that's what we learned a long time ago, right? In the previous lecture. Okay? If there's no flips, and we want constructive, the only problem is the path difference. But if the path difference is just a wavelength, or 2 wavelengths, or 3 wavelengths, we're guaranteed to get constructive interference. So the condition is the path difference, 2t, equals an integer times the wavelength of light in the film, right? Because this is where the path difference is occurring. It's in the film. All right? So there you go. No flips. Path difference is m lambda film. That's all. Now, obviously, you can't have m equals 0 here, because if m would be 0, you have the path difference of 0, which would mean there's no film, so that's sort of a pointless thing, right? Okay. All right. I hope that makes sense. Now, so this should make sense, this row. Now let's do the second row. Okay, well, first let's think about it. Okay, now let's say that there's one flip. And I don't care if it's at this reflection or this reflection. But one of those reflections, there's a half a wavelength flip. Okay, now think about it. Let's just say there was no path difference, but there's a wavelength over 2, there's a lambda over 2 flip. How is that going to interfere? If there's no path difference and there's a lambda over 2 flip, it's a destructive, right? It's going to it's going to interfere destructively, right? Destructively. But come on, we want constructive, all right? So right now with one flip, we're dead. Because with one flip, we have a lambda over 2 path difference, right? That's what it's equivalent to, a lambda over 2 path difference. And that's going to kill us. It's going to get destructive. Wow, hold it. We can take care of that. What if we make the path difference a half a wavelength? Or 3/2 of a wavelength? Or 5/2 of a wavelength? You see? Because if this is a half, and then we make the, okay, this is from the flips, whatever. Okay, so the flips gives you delta x equals this. Now, if the literal path difference, the 2t, that's a delta x, right? If that's like a half a wavelength, or 3/2 a wavelength, or 5/2 wavelengths, or whatever, what's the total? The total is going to be 1, 2, or 3, right? And that's going to guarantee constructive interference. Agree? All right, so what I'm saying is then that 2t has to be this. So 2t has to be half, 3/2, 5/2. Now, we're going to write it in a cool way. So how are we going to write it in a cool way? I mean, just like this. Okay? So let's see if it, all right, let's see if it makes sense. So we want the 2t equals m minus a half wavelength. All right, so if m is 1, 1 minus half is a half, half a lambda. Got it. If m is 2, 2 minus a half is 1, 2 minus 1 half is 3 halves, 3 halves. Got it. If m is 3, 3 minus half, 5 halves. Got it. Okay? So it works. Now, notice, you don't have to say m minus half. You could have said m plus a half, but then you would have started out at 0. But for this guy, we started out at 1, so we kind of want to just keep it consistent. But again, all I'm saying, you don't have to say m minus half. You could say m plus half. Just start with different m's. All right? So this makes totally sense, right? So this introduces a half wavelength. This introduces half wavelength, or 3 half wavelengths, so we're going to guarantee to get constructive. If this is not making any sense to you, you better think about it, because it has to make sense. Okay, now let's say we have 2 flips. So this guy flips, and this guy flips. Well, if they both flip, what's the net result? Nothing. Right? Because one guy flips a half a wavelength. I mean, remember, it's the same wave. This is a half, that's a half. What's a half and a half? 1. So this is basically the same as that. Right? So we just get that. Ta-da! Okay, now, honestly, I'm not joking. You make sure you totally understand this, because I am not going to give you this on a test, and I think you're crazy if you memorize it. You have to understand it. All right, let's do destructive, all right? So now what we want to say is we want to guarantee that 1 and 2 interfere destructively, okay? Guarantee that. All right, so let's do it. Okay, so the first one, these are the only possibilities, right? No flip, 1 flip, 2 flips. Okay, so if there are no flips, well, that means, if there's no flips, that means that they're on the right path, right? I mean, they're the same, except for the path difference, right? If there are no flips, the only thing that's different about 1 and 2 is the path difference. Agree? Because 2 is traveling 2t more than 1. So, we have a path difference, 2t. Now, we want destructive interference. So, what do we want that path difference to be? Well, half a wavelength, 3 halves, 5 halves, etc. Right? Right? That's it. How do we do that? Oh, sorry. Okay? So that's one way you can do it, right? So 1 minus a half is a half. 2 minus a half is 3 halves. 3 minus a half is 5 halves. Bingo, you got it, right? So this guarantees that will have destructive interference. To the next one. In the next one, we have 1 flip. Oops, we weren't supposed to see that. All right. So now we say we have 1 flip. Now I don't care if it's this one or this one. It doesn't really matter. If we have 1 flip, it's equivalent to having a phase difference of lambda over 2. Now, if it's lambda over 2, they're going to destructively interfere, right? Lambda over 2 means destructive interference. So we don't want the path difference to change anything. So we want the path difference, so we just want the path difference just to be lambda or 2 lambda or whatever, right? Because with 1 flip, it's going to destructively interfere. So there you go. Okay. Now with 2 reflections, that means we have 1 here and 1 here. It's the same as that, like always, right? Because this one flips lambda over 2, that flips lambda over 2. What's the equivalent? I mean, what happens when you have both of them flip lambda over 2? Nothing. So it's just this again. Okay, so I've said it at least 5 times. Understand this. Don't memorize it, because you're not getting it on a test for the equations. All right, now let's do an example. Okay, so everybody read the question, please. Okay, the first thing you want to do is draw the picture. I mean, you just got to draw the picture correctly. Okay, so you have plastic on glass, and there's air. So in my opinion, just do it, right? So here's air, here's the Notice it's not thin. I don't care, right? This is the thin film. Here's glass. So you're going to label them. So this is air up here, and there's what is the plastic, and then glass. And you always want to write down the ends because that's the important thing. So N is 1.52, N is 1.61, N equals 1. Yeah, you got to know N equals 1 for air. All right, so you got to do that. And this is like the pictorial representation that we did in Physics 121. You do this, you get it right. Hopefully. All right. Okay, so that's it. And again, this is the thickness of the plastic. So the thickness is T. T stands for thickness, huh? And I don't care about all those angles. Okay, so you have one light ray coming in, and it reflects. Then it goes through, and I don't care about the dumb angles, right? Don't worry about it. We'll learn about that later. It goes through the film, the plastic film, and it reflects, and then it goes back. So there's two, all right? So here's the first reflection, here's the second reflection. All right, so first you draw the picture. First you draw the picture, and then you draw your light rays, all right? And this is going out. So this is coming in, this is going out. Okay, now so you draw your picture, label it, draw your light ray, one light ray coming in, reflects, going through, reflects. Now you have to ask yourself all this business about the lambda over 2. So light ray number 1. Light ray number 1 goes from small n, right, to larger n. Agree? So it goes from air, and it reflects off of the plastic. So n equals 1 to n equals 1.61. So lambda 1, it flips. Lambda over 2 flip. So that's inverted, which is equivalent to lambda over 2 flip. Okay, now how about number 2? What does number 2 do? Number 2 goes from 1.61 to 1.52, right? This is plastic. N is 1.61. Glass, 1.52. So it goes to large n to small n. So there's no flip. No flip. Okay, great. Now, what do we want? Constructive or destructive? Well, let's see. You got to read it. So a layer of transparent blah, 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 blah. It looks dark when viewed in reflected light. So it says it looks dark. So what is that? Constructive or destructive? That's obviously destructive. So we want destructive interference. All right, that's the next step. You've got to figure out if it's constructive or destructive. Okay, now, this is great. Okay, I'm done with the picture. Well, I guess I shouldn't. Who cares? I need the room under my whiteboard. Look at that picture. Okay, so look at, we have a flip and a no flip. So right now, they're going to destructively interfere, right? If there were no path length difference, this would be a destructive interference, and that's what we want. So therefore, what do we want this path difference to be? In other words, right now we're going to get destructive interference because there's only one flip. So we don't want the path difference to mess it up. So we want the path difference to be like one wavelength, two wavelengths, on and on and on. Okay? So for destructive, which is what we want the 2T. Remember, I don't know why I didn't label it, but this is T, the thickness. So we want to keep destructive, so we want 2T to be I just say m lambda, right? You know, one wavelength, two wavelengths, da 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 da. Okay, now you got to be careful. The wavelength is in the layer, the plastic, right? Or the medium, whatever you want to call it. I'll say medium, and I'll say layer. You got to do that. You'll see why in a minute, right? All right. Now the question says the two smallest values for the thickness. Okay, piece of cake. So solve for thickness. So thickness is m lambda layer over 2. Whoopee! All right? Now here's something you can't forget. They tell us that the wavelength is 580